In this lecture, let us consider noise in angle modulated systems. So the model is as follows. At the transmitter, we have message m of t. This message is given to the angle modulator. Okay. Then we have the channel, which introduces the noise. Let us say the noise is additive noise n of t. Okay. At the receiver, at the front end, you have to select the signal, right? You have to select the signal of interest using a band pass filter. Therefore, after this, you must have a band pass filter. And then after band pass filter, followed by okay. So band pass filter, and then followed by you have a demodulator. Okay, so that is angle demodulator. And finally, you have the baseband filter, whose bandwidth is the same as message signal. Baseband filter, and the bandwidth is same as the your message bandwidth. Let's say W or B, not a problem. So this is the typical block diagram of angle modulated system. Okay, input message signal m of t given to angle modulator, and then finally the output of angle modulator is given to the channel. In the channel, the noise is getting added. Now we are interested in calculating the output SNR by calculating the output signal power and output noise power. So let's say output signal power and output noise power here. And from band pass filter to your baseband filter, this is called a receiver, and in between this is called a channel, and this one is transmitter. Now the important point is, like we cannot exactly proceed the way as we proceeded for the amplitude modulation, for two reasons. The first reason is that here band pass filter, what is the bandwidth of the band pass filter? It cannot be 2B. Okay, here the bandwidth of the band pass filter is different. This band pass filter has a bandwidth, okay, that is different as compared to the band pass filter that we had at the input to the amplitude demodulator. Okay, in the amplitude modulation, what is the bandwidth of the signal? It is 2B only. Okay, so this bandwidth is 2B, but here in angle modulation the bandwidth is not 2B. Okay, here the bandwidth is 2 times delta f plus its maximum frequency, let's say FM or W. Okay, so your angle modulated signal has much wider bandwidth. Of course, we are considering the wideband FM. So in this case, we are considering wideband FM, WB FM, wideband FM. So it has much wider bandwidth. So the FM receiver has band pass filter, but if you want to ensure that your angle demodulator receives an undistorted angle modulated signal, it must ensure that most of the significant components of the modulated signal pass through. Then the bandwidth of this band pass filter must be equal to the bandwidth of the modulated signal. Okay, so whatever the bandwidth is coming in here, in this point, whatever the bandwidth coming in here, that is coming out of the your band pass filter, must be allowed to pass through this band pass filter. So once you do the angle modulation, what is the bandwidth of your signal? That is 2 times delta f plus fm. So that much bandwidth should be available in this band pass filter. So that is the very first point. But your message signal has the bandwidth of b hertz only. But the moment you do the modulation, the bandwidth becomes 2 times delta f plus 2f. It is not equal to 2b. Please remember that. So the bandwidth of the band pass filter will depend on the peak frequency deviation of the angle modulator. So let's say this is my angle. Let's say the peak frequency deviation is delta f of this angle modulator. So that is one difference as compared to the AM signal. Okay, so bandwidth of band pass filter is different in FM than that of AM system. So that is the first point we need to understand. And the second important point is that the amplitude modulation systems are linear. AM systems are linear, like your DSB, SC, then SSB, then VSB, then AM with carrier. But if you apply for all of them, synchronous demodulation. Okay, and AM systems with what I say, envelope detector. And then FM, third one is, let's say, PM. This all are non-linear modulation scheme, or non-linear systems, I can say. Okay, so the amplitude modulation systems are linear, at least when we were discussing the synchronous demodulator. Okay, the moment you include envelope detectors, then it became non-linear, because there is a square root operations and things like that happening. Otherwise they were linear systems, because in envelope detector we found the envelope of the signal. Therefore we took the square root of your message signal plus in phase component and quadrature phase component. Please recall that from the previous lectures. Therefore we could actually use the principle of superposition for linear system. What do we mean by superposition? You can separately calculate S0 and you can separately calculate N0 and you can take the ratio. Okay, so that means we can calculate the effect of signal in the output and the effect of noise in the output separately. So that's what we mean by superposition. So you can calculate these two quantities independent of each other. Okay, similarly I can calculate the input power SI and I can calculate the input noise power separately, and then I can take the ratio SI by NI and S0 by N0. So the linearity implies that the ratio will be just the same, but this kind of things I cannot do anymore in FM system, because FM is not a linear system. Okay, so it is a non-linear system. So these are the two complications one has to consider when you do the analysis of FM system. Okay, so now let us proceed. Let us start with the modulated signal. What is our modulated signal? Let me call S of t is equal to A times cos of omega c t plus the phase angle. I am going to denote psi of t instead of phi of t, psi t, and this psi t contains what? The intelligence. Okay, some waveform which contains intelligence of the message m of t. Okay, Now what is psi of t? Psi of t is equal to 2 pi k suffix f integral of m of tau d tau, and the limit is this one. This is for FM system, if you are working with the frequency modulated system. In case if you are working with the phase modulated system, then this is going to be k suffix p times m of t. Recall this. What is m of t? M of t is the message. So this is the model in which you have to work now. So let us start from the very first point you have, that is white Gaussian noise has been added in the channel, right? So you have the m of t. M of t is given to angle modulator, and this one is given to the channel. In the channel, who is adding? The noise is adding n of t. Now what is this n of t? N of t is the white Gaussian noise. Right? And this n of t is given to the band pass filter. Output of the band pass filter, let me denote by ni of t. And at this point, what signal do you get? This is going to be a times cos of omega ct plus psi of t in this point. So both are getting added. Sum of this guy and sum of this guy will appear in this point. Then the output, the band pass version of your white Gaussian noise. What is ni of t? Ni of t is the narrow band noise. Narrow band Gaussian noise. Output of the band pass filter. Once again, you are getting narrow band noise, but this narrow band noise has a bandwidth which is much wider, because this band pass filter is designed to have the bandwidth of 2 times delta f plus fm. For example, we have done the simple calculation for our FM system. For commercial FM, this is going to be 75 kilohertz, and this is going to be, let's say, 15 kilohertz highest frequency. So this is equal to 180 kilohertz, much wider bandwidth. So this band pass filter has very high bandwidth compared to the bandwidth of your message signal. What is the bandwidth of our message signal? It is only 15 kilohertz. Okay, so it is simply 15 kilohertz, but your band pass filter has a bandwidth of 180 kilohertz. So therefore the narrow band noise has much wider bandwidth. So that is the key point that we need to understand here. Now after this is given to the demodulator. Okay, if you go back to the block diagram, you can see that angle demodulator. Output of the band pass filter is given to angle demodulator. So you put a angle demodulator. So in this point, I need to calculate Si and n suffix I. So therefore, at the input of angle demodulator, what do we have at the input, at the demodulated input? I am sending this ni of t. What is ni of t? Narrow band Gaussian noise. So this narrow band Gaussian noise can be written in terms of in phase and quadrature phase component. So n suffix c of t times cos of omega ct plus n suffix s of t sin of omega ct. And here this suffix I refers input to the demodulator. Okay, I refers after the band pass filter and input to the demodulator. And narrow band noise will have this representation, in phase and quadrature representation. So as far as the representation is concerned, there is no difference. The representation is still valid. But this is a band pass process with the power spectral density function, which will be denoted by, this is a band pass process, band pass noise process, and with the power spectral density Sn of omega. The important thing is that this power spectral density function will have the bandwidth. What is the bandwidth? That bandwidth is equal to 2 times delta f plus b. B is the message signal bandwidth. So this is my bandwidth, where delta f is the peak frequency deviation of the modulator. So whether it is FM modulator or PM modulator, this delta f is nothing but peak frequency deviation. And alternatively, we can also write this Ni of t in terms of its envelope and phase angle. Therefore, this n suffix I of t alternatively can be written as envelope denoted by E suffix n of t times cosine of cos omega ct plus theta n of t. I am going little slow because this noise analysis in FM system is quite complex, so I don't want to rush through and make it very fast. Now what is your En of t? Envelope of your quadrature representation, and this is equal to its amplitude nc square of t plus n square of t. And what is the phase associated with this? Theta n of t. Theta n of t is equal to tan inverse of quadrature component, that is ns of t, divided by in phase component nc of t. And this n indicates noise, subscript n indicates noise, and this subscript also indicates noise. Okay, so far so good. So this becomes like this, and where En of t is this one and theta n of t is this one. Okay. Now before we proceed, one point I would like to understand. The fact is that this noise has the bandwidth of, as I said, 2 times delta f plus w, whereas the message has the bandwidth of b. So noise Ni of t has the bandwidth of 2 times delta f plus b, but message m of t has the bandwidth of b hertz. That means the noise that you are considering at the demodulator input has much larger bandwidth. Okay, typically this is, as I said, typically this is equal to 180 kilohertz, and this is typically for FM system 15 kilohertz. Therefore, if you take delta f alone, it is greater than beta b. Okay, so you have to ensure that the bandwidth of this band pass filter here, this band pass filter is equal to the bandwidth of the FM signal or PM signal. What is the bandwidth of FM signal? 2 times of del f plus FM. So whenever you are designing this band pass filter, the bandwidth of this band pass filter must be equal to the bandwidth of FM signal. Otherwise, you will not get the proper output. If you don't ensure this condition, then what will happen? Your angle demodulator is not going to get the right kind of input for demodulation, because your modulated signal has that much bandwidth. If your band pass filter doesn't have that much bandwidth, then what will happen? Some portion will be cut off, and the demodulator will not do the do the demodulation properly. I mean the demodulator will not get the right kind of input, right kind of angle modulated signal or proper angle modulated signal. Therefore, the bandwidth of this band pass filter must be equal to 2 times del f plus b. Whereas the bandwidth of your message signal is b hertz. Please remember that. That's all I am saying now. But the modulated signal and the noise which are going to the demodulator both have the bandwidth of 2 times of delta f plus b. So one more point I would like to write here. Modulated signal. Okay, so this one is S of t, and this S of t has the bandwidth of how much? 2 times delta f plus b. So these are the 3 points we should remember. The noise has a bandwidth of 2 times del f plus b, modulated signal has the bandwidth of 2 times del f plus b, and the message has the bandwidth of only b. Okay. Now what is the implication of all these things? The implication of this is as follows. Now let us look at the modulated signal. S of t is equal to a times cos of omega ct plus psi of t. Okay, this signal S of t also has the same bandwidth. What is the bandwidth? 2 times of delta f plus fm. Okay, let me say this is equation number 1. Okay, the signal which is reaching, shall I draw the diagram or? Okay, let me draw here one more time. M of t, angle modulator, and then channel, noise is getting added N of t, then band pass filter. Let's say this is point A, and here you put an angle demodulator AD, and then put a low pass filter, band pass filter. That's it. Let's say this point is A. Now what I am saying is, this signal S of t, when it reaches the point A, then that point A also, at that point A also, it has the same bandwidth, and noise also has the same bandwidth. And here also the modulated signal has the bandwidth of 2 times del f plus fm, and in this point also the modulated signal has the bandwidth of del f plus, let's say, b hertz. That would be more appropriate. B hertz, 2 times delta f plus b. And here the noise also has the bandwidth of, this is modulated signal at point A, and the noise also 2 times delta f plus b, your narrow band noise. Both of them have the same noise. Now the message is not embedded in S of t, the message is embedded in psi of t. Okay, so the message has the bandwidth of b. What it means is that this equation 1, you are adding to the noise. Okay, what you are seeing here, what you are seeing at point A is not only the message but plus the noise, narrow band noise. So that is the important point to note. That is the important point to understand here. If you look at the sum of these two things, the signal has a very large bandwidth, noise also has the very large bandwidth, but your message has the very small bandwidth. So at point A, let me write down yi of t. So this is at point A. At point A is equal to yi of t, that is your signal S of t plus ni of t. What is S of t? From equation 1, S of t is a times cos of omega c t plus psi of t. What is Ni of t in terms of quadrature representation? Nc of t cos omega c t plus Ns of t sin, or else let me write down its envelope representation. So En of t cosine of omega c t plus theta n of t. Now look at this equation. This is my signal part and this is noise part. Now the signal has the bandwidth of 2 times delta f plus b, 2 times delta f plus b, and this noise also has the bandwidth of 2 times delta f plus b. Where is the message? The message is hiding here in the psi component, okay, because psi of t is proportional to m of t for Pm and proportional to integral of m of t and dt for Fm. Therefore, this psi of t has the bandwidth of how much? B hertz. Okay. Therefore, the signal component has a bandwidth of 2 times del f plus b and the noise has very large bandwidth of 2 times del f plus b. But my message signal psi of t has the bandwidth of B hertz. Okay, so that's it. Now let us talk about phase modulation. Same structure. Phase modulation. But here psi of t is simply equal to Kp times m of t. That is the only difference. Noise is remaining the same. The noise is again, it has the envelope En of t and theta n of t. As far as noise is concerned, no change. But as far as the signal is concerned, only psi of t is replaced by Kp times m of t. So at the input to the system, the signal has the instantaneous amplitude which is constant A. Therefore, and it has instantaneous phase, that is psi of t. And the noise has an instantaneous amplitude, that is En of t. And it has instantaneous phase which is theta n of t. Therefore, my signal component is A times cos of omega c t plus theta n of t for signal as far as signal is concerned. I am sorry, this is not theta n of t, it is psi of t. What is psi of t? Psi of t is equal to Kp times m of t. And this is my instantaneous amplitude. Amplitude of what? Modulated signal. And this is the instantaneous phase. Phase of modulated signal. Similarly, for noise, I have E suffix n of t cos of omega c t plus theta n of t, and this is instantaneous noise amplitude. Okay. Instantaneous noise amplitude. And this one is instantaneous phase amplitude. Instantaneous phase, that's it. So basically I am trying to compare A and psi of t with the E suffix n of t and theta n of t. That's what I am going to do now. Okay. Anyway, A is a constant. Even if it is constant, then how will you make it constant? By using band pass limiter, hard limiter followed by low pass filter or band pass filter. And what is psi of t? Psi of t is proportional to m of t for the case of PM. For phase modulation, it is psi of t is proportional to m of t. Now what I am saying is this En of t, the instantaneous amplitude of noise, and theta n of t, the instantaneous phase angle, have the bandwidth proportional to delta f plus fm. See, my psi of t has a bandwidth proportional to b hertz bandwidth. Bandwidth is equal to b hertz for my psi of t. And this A is a constant. Even if it is constant, no problem, I can make it constant. But here this En of t and theta n of t, both of them has very large bandwidth. That bandwidth is proportional to or equal to 2 times delta f plus fm. That means what? This is after all 15 kilohertz and this is 180 kilohertz. So who is varying much faster rate? My noise component is varying at a very fast rate. Okay. Therefore, the noise component En of t and theta n of t will vary much more rapidly than your psi of t, because psi of t is directly proportional to m of t and m of t has the bandwidth of 15 kilohertz. So this is the important point we need to understand. So therefore, psi of t has the bandwidth of b hertz, and this En of t and theta n of t, both of these guys has bandwidth of 2 times delta f plus b. Okay, and these are low pass signals. Your message signal is a low pass signal. Okay, so therefore, since the bandwidth is higher, this En of t and theta n of t will fluctuate much more quickly. Much more quickly than that of psi of t. Okay, so that means you can think of the phase of the carrier which contains a message, more or less it remains constant over several cycles, whereas the corresponding phase of the noise would have undergone very wide fluctuations. Okay, so let me write down the statement and again I explain this. So if I go a little fast, it is difficult to understand. A times cos of omega ct plus psi of t, and then you have e suffix n of t cos of omega ct plus theta n of t. What I am saying is, you take a small interval of time, let us say capital T seconds. In this capital T seconds, your psi of t is almost constant, but psi of t is also changing. But if you take very small duration where t is very small, if you take some small duration, in that duration what will happen? Psi of t is nearly constant, but your theta of n of t would have undergone many more cycles. Okay, so very wide fluctuations, that's what we are trying to say. So this guy fluctuates slowly and this guy fluctuates very fast pace. So compared to theta n of t, you can assume that psi of t is constant, because for a small period of time the value of psi of t is nearly constant, but in that time the carrier goes through many cycles. So you have many cycles of the carrier, but the value of psi of t is nearly constant, because psi of t is equal to kp times m of t, because where m of t is 15 kilohertz signal only after all. But your theta n of t would have undergone many more cycles. But all are low pass signals only. This En of t, theta n of t and psi of t all are low pass signals. But this has a bandwidth of 15 kilohertz and this guy has a bandwidth of 180 kilohertz for a commercial FM. Okay, therefore I am comparing three low pass signals, psi of t, then e suffix n of t and theta n of t. So the psi of t has, let's say, the bandwidth of minus 15 to plus 15 kilohertz, and this theta n of t and en of t has the bandwidth of, let's say, minus 180 to plus 180 kilohertz. Okay, En of t and theta n of t both are noise. This represents En of t and theta n of t, and this represents your psi of t for FM. That means what? En of t and theta n of t, see, this is frequency domain representation. Okay, it is frequency domain representation. If you take time domain, more number of cycles in a small duration, very fastly it is fluctuating. But your psi of t, it varies. Maybe I will draw in this different color. It goes like this, like this. This is slowly varying. Your psi of t in the time domain, and this is your theta n of t, and in fact I can say En of t in the time domain. Time domain, for a given time interval you have large number of cycles, but the psi of t has slowly varying. In the frequency domain, it is, since it is slowly varying, the frequency is less. That is why you have limited bandwidth, small bandwidth. But the noise has huge amount of bandwidth. Okay, psi of t will fluctuate less rapidly, and e suffix n of t and theta suffix n of t will fluctuate more rapidly. So this is the key point. Keep in mind as you proceed. Now, how do we calculate the output SNR? We cannot calculate the output SNR the way we calculated for amplitude modulated systems. Why? Because AM systems are linear modulation. In AM system we use linear modulation, but here it is a non-linear system, so we cannot use the linearity principle. Okay, so in that sense, what? We cannot consider the linearity principle. For FM and PM. Why? Because they are non-linear. When I say linearity, what does it mean? You can calculate noise alone and noise power alone and signal power alone. Okay, linearity means that is what your superposition theorem, right? You can calculate noise power alone, these are important points, and signal power alone, but that cannot be done in this case. So in FM and PM we cannot calculate, we cannot consider noise alone, and we cannot consider signal alone. Okay, so the best thing to do is start with the sum of these two guys, S of t plus N of t. So which is what you will have to you will have at the demodulator input. Therefore at the demodulator input you have these two guys coming together. So your yi of t, this I already wrote, a times cos of omega c t plus psi of t, then plus ni of t. Okay, now a times cos of omega ct plus psi of t, and what is ni of t? E suffix n of t multiplied by cos of omega ct plus theta suffix n of t. That's it. Now to proceed further, it is best to understand the nature of signal part and the noise part through the diagram, something called a phasor diagram, because you have two cosinusoids differs by phase. One component has this phase and another guy has this phase. Therefore, it is best to describe or best to understand the nature of these two guys through the phasor diagram. So let us try to draw the phasor diagram. Okay, now the phasor diagram that we discussed earlier, that are going to be very important now and very useful to carry out this analysis. Okay, let's remember the basic points now. So let's say this is my reference point. Let me put a reference axis. Okay, reference phasor. At some time instant t, what is the instantaneous carrier phase? It is omega ct plus psi t, some time instant, let's say t1 or t something. Therefore, let me draw a phasor with a certain angle. This is omega ct plus psi of t, and this vector length is how much? A. Okay, so let me denote like this, the length of A, maximum vector length. So if you are assuming that the whole system is rotating at omega c radians per system, then you can simply write psi of t, right? You can write, because you can cancel out this omega c, and then simply you can write like this, and let's call this is my psi of t. Any one you can choose, either you can choose this or you can take that one. Okay, otherwise you write omega ct plus psi of t, and the amplitude is A. Okay, to that what you are adding? You are adding the noise component En of t times cos omega ct plus theta n of t. What is the phase angle associated with the noise component? At some particular time instant t, omega ct plus theta n of t. Therefore, you are adding the noise component like this. This is my En of t, and if you extend this line, this is the angle associated with the noise component, omega ct plus theta n of t. Okay, and the instantaneous amplitude is En of t. Let me E suffix n of t, and the angle is associated with the noise component is omega ct plus theta n of t. Now theta n of t is measured with respect to the reference axis in the clockwise direction. Now you add this vector, let's say this is origin and this is En. Let's say this point is some x and this point is y. You add these two vectors, ox and xy vectors, because we are adding the two signals. The sum of these two vectors, let me call, this is my sum of these two vectors like this. This resultant vector, let me call by r of t. So the amplitude of that vector sum is r of t. So I can write the input signal y suffix I of t as its amplitude and cosine of its angle. What is the amplitude now? R of t, and cosine of its angle. What is the angle now? We need to calculate. So that angle is going to be this angle. What is that angle? Let me say this angle is del psi, delta psi. Okay, so let me call that angle as a delta psi. Now what is this angle? This angle is going to be this angle plus this angle. So the total angle is equal to omega ct plus psi of t plus delta psi of t. Therefore, the resultant signal is written as its resultant amplitude r of t times cos of, everybody is rotating at the rate of omega ct plus the total angle. What is the total angle? Psi of t plus delta times psi of t. Okay, so it is clear that effect of noise is sitting over in this position. This is due to noise. Why is it due to noise? If you look at the figure, then it will be very clear. Okay, where is the effect of noise is going? It is going in r of t. Look at the figure. Okay, it is going in r of t to some extent and going in del psi t to some extent. In case if En of t is equal to 0, then what would have happened? So you have the reference signal and this is my A and this is my En of t, right? And if this En of t is not there, so therefore this is my amplitude. In this case, this is the same as your r of t, and in this case, what is your delta psi of t? Delta psi of t is equal to 0. Okay, so delta psi, if the noise component is not there, then delta psi, this angle, maybe I can use a different color. This angle becomes 0 if delta psi of t is 0. Okay, if the noise component is 0, then this angle will not be there. The resultant r of t would be the same as this line. That's what I am saying now. Therefore, the noise will affect r of t as well as your delta psi of t. Both are affected by the noise. Okay, this guy also affected by noise. And this also affected by noise. If En of t is equal to 0, then what will happen? Your r of t is the same as A, and your del psi of t, this extra phase angle is 0 degree. Okay, so that is very important point we need to understand. So this is my input signal to the demodulator. So the time variation in this would not be matter. So we no need to consider the time variations, because you remember the demodulator will also contain a limiter. So this r of t will be converted into a constant amplitude, that doesn't matter. So there is of no consequence. So really speaking, the angle demodulator will produce an output proportional to the instantaneous phase angle. What is the instantaneous phase angle? This guy. So demodulator output is proportional to psi of t plus delta psi of t, and this delta psi of t depends on the noise. So the effect of noise will be obtained by considering the effect of noise on psi of t. So psi of t is what you should not have got, which you are getting because of the noise. Okay, and that you can see from the Phasor diagram. So once again, to proceed further, we have to consider two situations separately, as we considered in the amplitude modulation, right? In the amplitude modulation with carrier, we have taken two cases. The first one is synchronous demodulator, and the second one was envelope detector. In the envelope detector, we consider two situations. Okay, so that means what? One is large noise condition and another one is small noise case. Okay, here also we are going to consider two cases, small noise case and large noise case. Here also we will consider two noise cases. Okay, now this then we will proceed, and a small noise case means what? Your signal power is greater than the noise power, and here the noise power is greater than the signal power. Okay, then if you don't consider this kind of assumptions, then we will not be able to complete it. Okay, we will not be able to calculate the output signal to noise ratio easily, so it will be quite complicated. So let me stop at this point. In the next lecture we will consider these things. Thank you very much.